Good morning, everyone. So up to last class, we have discussed the theory of MLPs. We discussed some of their merits and demerits. We also looked at some applications. These are more artificially oriented applications. We only looked at some behavioral aspects and how the network can reproduce some of the behavioral and aspects of of humans engaged in certain simple tasks like reading and learning past tense and things like that. But let us now go deeper and see if there is greater biological realism about the way the MLPs work or the way they are trained using backprop algorithm. So let us look at the biological plausibility of both the algorithm that we use to train an MLP, right, and also the MLP itself, the way it learns a task, right. It might be able to reproduce some behavioral aspects, but the way it solves the problem, the kind of representations it generates internally, are these also biologically realistic? So let us look at that. The first question is discussed very well in this recent review by Whittington and Bogas. It's called Theories of Error Propagation in the Brain. It's a recent paper, 2019. So I'll just discuss one. So there are many architectures that have been proposed, that are more realistic and more biologically realistic than backprop. So I'll just talk about one of them. So basically, these authors argue that the main drawback of BPA algorithm are the following. Um, so first of all, the lack of local error representation. So what does that mean? So if we have a three-layer network, right, it applies to any number of hidden layers, but we have a three-layer network. Input is given here. This is output. So error is available at the output because you calculate E is equal to D minus Y. Okay, and then delta is, is also kind of delta comma E. This is slightly more complicated because you also have that gradient derivative term, G prime term. So the error is available at the output, right? The error is not easily available at the hidden layer. We made up something, we defined something called deltas, but normally the error is available only at the output. So this is one problem. But the way we make error available at the hidden layers is by backpropagating the error from the output layer, right? For which we did something interesting. We said we can take the errors at the output and backpropagate it by the same weights to the hidden layer. So we call this delta second stage. We call this delta first stage. Delta first stage is computed by linear sum of this deltas at the output with the second stage by backpropagating it over the same weights. The thing is, normally, so we said last class also, the neurons are, a synapse is unidirectional. Right, when the action potential comes here, the neurotransmitter is released from here, right, and receptors on this side. So transmitter release from presynaptic side, receptor, and transmitter, binding with the transmitter on the postsynaptic side. So there is a clear pre and post distinction. So the synapse is an asymmetric entity. So therefore, I cannot use the weight in both directions. That's biologically not realistic. But that's what we are doing here in backprop. This is one big question, and not only that, right, having backward weights is one thing, and requiring that you should have the same set of weights. That is, you have to have the same values of the weights even in the backward direction, which is quite artificial. The last thing is that it's an unrealistic model of a neuron because we just say that, right, neurons simply compute linear sum of the input, and if the linear sum crosses a threshold, you produce some output y. Okay. So that is also a bit artificial, but the last one is not a big problem and we can live with that, right? And neurons indeed behave approximately something like that if you take averages over time and ignore the spikes. Because the only thing that the real neurons show, compared to a McCullough and Pitts neuron or a sigmoid neuron, is that real neurons show spikes. But this is a rate-coded neuron, so I think we can live with this. Last one is not a big problem. The first two are still serious problems. So considering these kinds of objections about BPA algorithm, People have presented a large number of architectures, and this paper, discusses a lot of them. But I'll just talk about one particular solution, just to give a flavor of what kind of things have been said, right, or offered as a solution to the artificiality of the BPA algorithm. So if you want to construct a biologically plausible learning algorithm, right, how do you deviate from BPA algorithm? First of all, what happens actually in the real neurons? How do real neurons learn? Right. So this question has been around for quite some time. So way back, so in this book called Organization of Behavior, written by Donald Hebb and published around, I think, 1949, he has taken up this question. So because we know that brain can learn, but what is the cellular substrate of that learning, right? So when you learn, what happens at the level of cells, right, to capture the results of that learning. So Hebb proposed in this book very insightfully that when the axon of a cell A, so this is his exact language. So if you have cell A, and this is its axon, this is its terminal, this is the button or some other neuron, and okay. So when axon of a cell A is near enough to excite a cell B, and repeatedly or persistently takes part in firing it, some growth process or metabolic change takes place in one or both cells, such that A's efficiency as one of the cells firing B is increased. That's a kind of convoluted language, but essentially what he's saying is, if A succeeds in exciting B and it does it repeatedly, so something must happen in the synapse so that it becomes stronger. So what that means is, so to give like a little narrative of that, so A gets activated, right, and in response, B also gets activated. I don't know how do you show that, so I can show you. So B also produces action potential as a result. When that happens, right, the synapse must become stronger. Okay, the synapse must become stronger. What does that mean? Next time when you give the same kind of action potential, the PSP on the postsynaptic side must be higher. Okay, so than before. So we'll say before learning. Before learning, I have neuron A, I have a synapse, I have neuron B. I give a single action potential, and on this side there's a tiny PSP. So this is before learning. So then we say during learning. So during learning, what happens? So A is supposed to repeatedly or persistently take part in firing B, right? So how does it do that? It produces, it sends out lots of action potentials, high frequency. Okay, and that will produce lots of PSPs, and so on. And because of that, B also now fires a lot. This happens for some time, let us say. Now you say, so then because of that, something happens in synapse. I just say, indicate this by this arrow to say that the synapse has become stronger. So when that happens, if you probe the same synapse after learning, right, I send again a single synapse just to test how strong the synapse is. This time around, the PSP is much bigger. I'm exaggerating a little bit, it's a cartoon picture. So you see that before learning, when there's a single action potential on the presynaptic side, there's a little blip and in terms of PSP on the postsynaptic side. But because of learning, but to produce this learning, what we have done is, we made sure A gives out a high frequency series of action potentials, sends it to the synapse. Synapse produces lots of PSPs, and which succeed in making B produce lots of action potentials. When this happens, that is, A is active, B is active. Okay, when that happens, the synapse becomes stronger. And how do you know it's stronger? right? After that session, if you again test it with a single action potential, the PSP produces even strong, even higher than before. So this kind of a thing, HAP set could be happening. It's only hypothetical, right? So the same thing can be described in simple language like this. When two neurons are simultaneously active, the connection between them must be strengthened. When one of them is active while the other is inactive, this connection between them must be weakened. So here we only looked at the case where both are active. But imagine a case, the kind of converse of this statement. So A fires, right, a lot, and B doesn't respond for some reason because synapse is weak, so it doesn't produce much PSPs. Then what will happen is the synapse is opposite, actually becomes even weaker, right? And A fires a little bit, but B fires a lot because of input coming from some other neuron. Because B doesn't get input only from A, it could be getting input from another neuron C. So C activates B, therefore B fires. A sends only a small number of action potentials. So then what happens is A is inactive, but B is active. That's also not good for this synapse AB. So AB becomes weaker. Right. So this is called Hebbian learning because it was proposed by Donald Hebb, and this is more kind of comically described by this statement: neurons that fire together, wire together. So we'll discuss this in more detail later on when we talk about Hopfield network from next week. So this can be written like this, right? If A is active, B is active, then this is, I'll call this W, right? And delta W must increase, must be positive. Okay, so delta W is positive. A is active, but B is not active, not very active. Then delta W is negative. So similarly, A is not very active, but B is active. Okay, because B gets inputs from some other neuron. Okay, and so that's also bad. So therefore, delta W is negative. And both are inactive anyway, nothing much happens. So basically, this is called Hebbian learning. So there is some kind of a, you see that when this happens, delta W seems to be dependent on both, on joint activation of A and B, right? So that is therefore normally described as XA times XB. Activation of A is called XA, activation of B is called XB. So when both are 1, it is positive. Even if one of them is 0, it is not negative, but it is 0. Nothing much happens. So if you want to capture that, I can have a small negative offset term just to capture that when one of them is 0, other is 1, right? You still have some delta W. You will have delta W which is negative. So these kinds of learning rules have been proposed. Lots of variations of the Hebbian learning have been proposed. These come under the general category of correlational learning. Right, so this is called Hebbian. So in general form, if I have delta W dependent on XA, XB, this is called Hebbian learning. And so this kind of learning has actually been observed in real neurons. And so that it corresponds to what is biologically called long-term potentiation. And so both aspects of Hebbian learning, that is, when both are active, W should be strengthened. When one is active, other is inactive, W should be weakened. Okay, so this first one corresponds to what is called long-term potentiation, and second one corresponds to what is called long-term depression. So I'll talk about this in more detail in the next few classes when we discuss the Hopfield network. So anyway, this kind of learning is called Hebbian learning. People have also observed the opposite of that, where delta W depends on, in some synapses under certain conditions, because this is biology. For every rule, there is an exception. So this is, delta W is minus or proportional to the minus of XA, XB, the product. And this kind of learning rule is called anti-Hebbian. Both Hebbian and anti-Hebbian learning are biologically realistic. So this is given. But like we discussed before, what happens in backprop is quite artificial. So what happens in backprop, it's summarized here. This is from the paper by Whittington and Bogarts. So here this is X1 is the first layer, X2 is second layer, X3 is the output layer. It's given in vector and matrix form, so that you can have a compact notation. So basically XL, the activation of the Lth layer is simply the weight matrix multiplied by the activations of the L minus 1th layer. That's a simple recursive feed-forward computation. Then finally, when you go to the last layer, which is X capital L, right, the activation of that is compared with the target value or desired value T, and T minus XL norm square is the cost, is output error. Now, how do you calculate the weights? Delta WL depends on these deltas, right, the error deltas. Delta L plus 1 times F at XL transpose, the product of these two, which gives you like its outer product of these two vectors, which gives you the update for the weights in the layer just below the deltas, because the delta is at L plus 1th layer and WL corresponds to the previous one between the output, that L plus 1th layer and the previous layer L. Now delta L for the last layer, it is T minus XL. The previous layer, it is given recursively by back propagating the weight, so it is given delta at small l is given as W transpose capital W transpose L times delta L plus 1. So you take deltas at L plus 1th layer and pass it through the weights at L, and you get the delta L small l deltas. So this is a summary of backprop in more compact notation. And this is where we have objection, right? We said this is biologically not realistic, because how can you just backpropagate errors for the same set of weights, because weights are in one direction. Now the thing is, one of the common anatomical features of the brain, right, is very often if a part of the brain, call it A, this is not a single neuron, we're talking about a patch of the brain, projects to another patch B. This patch B in turn sends feedback connections to A. This is very common in the cortex, for example. There are also deep subcortical loops, right? Cortex, neurons in cortex projecting to nucleus 1, which projects to nucleus 2, which projects to nucleus 3, and finally returning back to the cortex. These kinds of loops are also very common between the cortex and subcortex. So in this architecture, this is a small variation of the previous one. The previous one is a completely feed-forward architecture, which is what the original backprop is based on. Now consider a slightly different architecture, where the input layer projects to X2, hidden layer, and X2 projects to X3, but X3 sends feedback to X1. In fact, this is quite common in the brain. This is somewhat artificial, right? But this is actually quite common, because if you look at a visual system, for example, or auditory system, we'll look at both these systems in a minute in this class. If you think of X1 as the eye, which is the input, right? Input layer is the eye, the retina. From there, you send projections to the next stopover in the visual system, which is a part of the structure called thalamus, and specifically a part of the thalamus called lateral geniculate nucleus, or LGN, right, is the stopover of the visual information from the retina, the first stopover. And from there, the LGN neurons send projections to the primary visual cortex in the cortex, the first stopover in the visual cortex. Here it's like X3. But the visual neurons and neurons of the primary visual cortex also send feedback to LGN. So this is actually identical to what happens between the input and the first two layers in the visual system. In the visual system, there are a lot more layers, right? And we'll also look at that later. But this is more realistic. So consider a network like this. And the only thing is here the weights in the forward direction, weight in the backward direction are the same, since that's symmetric. That is the weight matrix. So here is a transpose of the other. Okay, so if you assume that, so then what they are saying is take that the dynamics of a given neuron, right, a state of a given layer, right, XL dot is, so imagine if you have more layers, then you get just, you can have more general notation like XL. Okay, so XL dot is given by, so because a given neuron in a given hidden layer gets inputs both from the layers below and layers above, because we have inputs coming from both directions. So therefore, WL minus 1 times XL minus 1. This is like your just your previous feed forward connectivity. This is the feedback connection, and this is not delta. This is activations themselves are coming back. That is WL transpose XL plus 1. And it also says, okay, have minus XL as some kind of decay term. Now, if you go to the learning for X2, right? It is what we do normally is in backprop here, right? T minus XL. So here, let's say XL is the last layer is X3 for concreteness. I take delta W2 in the feed forward weights. It is T minus X3, right, times X2 transpose. Okay, so this is what we do for the W2 weights. Now this is where the trick comes. You split this expression, this error term, into two parts, right? Tx2 transpose, right, with a plus sign, and minus x3 x2 transpose, right? So therefore there's a minus sign. So you see that in both cases what happens is, so imagine that t is something that you give present as input. Okay. So this is x3. So where is this desired input or target input coming from? So I imagine that P is given as external input to this output layer, right? So that it can compare it with its internal state x3 and then come up with some error and things like that. So thing is, so x3 is its natural state, as in by influence of x2. T is the external input coming from outside, which defines the desired input. So now how do you, so if you use, right, if you invoke this term like tx2, right, now if t is given here and the activation here is just t, okay, then t times x2 is proper, that's Hebbian learning for the W2 connections. And suppose t is not given, x3 is simply under influence of x2, right, then x3 times x2, or x3 times 2 transpose with a minus sign is proper because it is anti-Hebbian learning applied to the same weights. So imagine a situation, it's kind of slightly artificial situation where I present t for some time, external input present for some time. During that time, x3 becomes t because I'm giving a strong input from outside. Okay, so and then x2 is still present because the input here is given. So now I'm training the W2s using the expression tx2 transpose, and that is nothing but Hebbian learning applied to these weights. Now I imagine that t is removed for some time, briefly. So then x3 is completely under influence of x2, that is x2 W2 W2 transpose. So then I apply Hebbian learning, but anti-Hebbian learning to the W2, that is minus x3 x2 transpose. So imagine I'm doing this alternately, present t for some time, train these weights using Hebbian learning, remove t, train these weights using anti-Hebbian learning. And if I do that, I'm effectively implementing the same learning rule. Okay, so it turns out that if you do that, and if you can accept the biological plausibility of this kind of a strange algorithm, that will give you effectively the same results as what backprop is. But we still have one problem here, which is that W2 is same. We're supposed to have symmetric weights. But what people have found is that it is enough to have some feedback weights. They don't have to be symmetric to the feed forward weights. That is, even if you have random feedback weights, if you have some feedback weights, that is enough, right? You can get about the same results as backprop. So this also people have found using a lot of simulations. So, and even this alternate presentation of T is also a bit artificial, because when you present a stimulus for learning, you don't flash it like you see a stable stimulus presented to you. So where is this kind of a flashing coming from? So what people have proposed for that is, is that brain converts that input stimulus, which is stably present, into some kind of an oscillation where the stimulus is presented like off and on in oscillatory fashion to the output. And such oscillations are present. They are biologically quite plausible. So there is one, so like that, there's one line of theory which tries to come up with a biologically plausible implementation of backprop. There are many others like that. So thing is, backprop is very exciting, very appealing, because it's a convenient learning rule. It follows the locality principle. You can train arbitrarily large feed-forward networks and all that. And it has some problems in terms of biological realism, but it's not a big problem because it gives enough motivation, right? Enough initial lead using which you can easily come up with extensions which are biologically plausible, right? So it's a good starting point and quite useful. So if you are interested, you can take a look at this paper. The paper talks about many such alternative or extensions of BP models, BP algorithm, which are biologically plausible. So much about the biological realism of BP algorithm. Now let us talk about the biological realism of the deep networks or MLPs in general. But I'm using deep networks and MLPs interchangeably because actually they are the same, right? Other than the hype and the fad, mathematically they are the same. So for this, my reference is Kell and McDermott. This is published in Current Opinion Neurobiology just a few years ago, about 2015 or so, I think. Such as deep neural network models of sensory systems. Specifically, they talk about visual and auditory systems and how deep networks have been able to explain the activation patterns of brain areas when people are engaged in simple sensory classification tasks. Okay, so the idea here is using DNNs to model sensory tasks performed by humans, and CNNs, that is convolutional networks trained on this task, have achieved human-level performance. In fact, sometimes and on some occasions they even beat humans and displayed what is called superhuman performance. But what is interesting is even at level of activations, they are similar to brain's activations. So this is just a schematic of a CNN, and we already seen CNN in the last class. Now let us say we train CNN on some visual pattern recognition task. Right, you want to recognize that the input image is a cat or a dog or something like that. Now, what happens in the brain, right, when you look at a visual pattern and you're trying to classify? So the journey of light in the brain goes something like this. So light first enters your eye through the small aperture here, the pupil, and forms an image. So if I have a tree here, okay, so because there's inversion, because it has to go through this kind of a pinhole, and it forms an image like in a pinhole camera on the retina. Retina has a first layer of sensors consisting of rods and cones. I think you will learn more about this in this a course offered by Dr. Santosh Setu Amanujam next semester, sorry. Right, he's an expert in retinal circuits. So, so the light information here is converted into electrical signals, pass through two layers of neurons right there within the retina itself, and output of the retina is conveyed by a set of cells called the ganglion cells, and these cells convey that information through a bundle of fibers, which is called the optic nerve. And this is the nerve which carries visual information from the eye to the brain. Optic nerve, goes to the first stopover of this information, which is the LGN, which is what I was talking about just a moment ago. So retinogenic nucleus is a part of the thalamus. So LGN then projects. So the retina has again two sets of cells called the M cells and P cells. So M cells carry more like motion information. P cells carry more like form and other information. So that segregation is roughly maintained even in LGN. So we have M layers and P layers and so on. So from there, information goes to what is called the primary visual cortex or V1. So up to here, this is thalamus, subcortex, this is retina, which is eye. So from this point onwards, this dash box, big dash box, that is the visual cortex. So you get into the cortical layers. So this is the primary visual cortex, located around what is called the occipital pole. right? Also called area 17. So brain surface, cortical surface divided into small regions called the Broadband areas. This is area 17. This is a number from I think 1 to 50 or 52 or something like that. Right, so this is area 17. Now, and after that you have this secondary visual cortex, which is area 18, and after that a few areas. But beyond this primary, secondary visual cortical areas, visual information goes via two important pathways. One is called the ventral pathway, and the other is called the dorsal pathway. The ventral pathway goes downwards into the inferior temporal lobe. You see that this is the temporal lobe. And the dorsal pathway goes upwards via the posterior parietal and more towards. Here you have these somatosensory areas and so on. So it goes upwards, right, via the parietal areas. So ventral pathway is involved. So the visual information is processed along two different pathways to access two different kinds of information. The ventral pathway looks at objects, classifies objects that are present in the input scene. The dorsal pathway is a bit harder to interpret, to see exactly what it does. But earlier they used to call it the where pathway because it detects or extracts information about the spatial information about the objects in the input image. That is, it determines where the objects are. But subsequently, forgot Mishkin and Ungerleider, I think, forgetting the name. So they propose that it's more involved in action, right? Visually driven action. So you can call it the how pathway. So where pathway slowly became the how pathway. But anyway, the interpretation of the dorsal pathway is not very clean. The ventral pathway is much cleaner. You can just say it recognizes objects. So from retina to LGN to V1 to a whole bunch of layers, right? This is called the temporal area, right? Which is in the temporal cortex, right? So this is the pathway which classifies objects. So this is the pathway which can be compared to a deep network. And here also in this pathway, there is a very logical, progressive, generation of representations present in the visual image. So for example, if you just probe neurons in the lowest layers in the retina and LGN, you will find that the neurons there simply respond to small dots. Because that means they are looking at really small parts of the input image. They can only see dots. It could be colored dots or black and white dots, or they're just dots. But if you go to V1, neurons now start looking at larger parts of input image. Just like in a convolution network, if you look at only the first hidden layer neuron, it responds to only a small part of the input image. But a neuron in the second hidden layer looks at a whole bunch of neurons in the first hidden layer. So therefore, it is effectively looking at a larger part of the input image. And this trend progresses as you go to higher and higher hidden layers. Therefore, neurons in higher hidden layers are able to see much bigger parts of input image. So therefore, they are able to interpret or respond to much more complicated patterns. For this reason, neurons in V1 respond to not dots, but lines, small lines, like with some specific orientation. And if you go to V2, which is a secondary visual cortex, you will find that neurons respond not just to lines, but they respond to the combinations of lines, because that's a generalization of a single line. You can call them angles, right? You can call them angles. You can call them it can be a combination of three lines forming some kind of, I don't know what you call it, like, so this is like a triple junction, right, and so on. Or it can also respond to, so one generalization of a line is straight line, a generalization of straight line is a curve. Okay, so a curved line basically. So they also respond to curvatures, curved lines, and so on. And as you go higher up along the dorsal pathway, you go to intertemporal area, you will find that neurons respond to complex objects. In fact, there is a whole distinct area within the infratemporal area called the fusiform region. So there you have neurons which respond to one particular class of complex object, which is faces. Because as humans, we deal with other humans more importantly. right? I mean, if people who are totally like nerdy and geeky or geekish, I don't know what's the correct word, deal with machines and objects all the time, mobiles and laptops and all that, but they don't like to talk to other people. But normal people, deal a lot with other people, so therefore, other people are important, right, in the lives of normal people. So in the brain also, there's a whole distinct area that represents face images that responds to facial stimuli. Okay, so now how do you compare, right, what happens in the dorsal pathway with what happens in a CNN? That's what people have done. So to that, so you cannot just take a correlation between a hidden layer of a CNN and some part of the brain, some part of the visual system, because I don't know how do you take correlation, because this CNN might have 1,000 neurons, hidden layer might have 1,000 neurons, and the corresponding brain area will have like 10 million neurons, something like that. So okay, how can you take a correlation? So what people have done is to understand the kind of a relationship between a given hidden layer in the CNN and a given part of the brain. They give a stimulus. Let's say I give a picture of a dog, a particular image of a dog to the CNN. It's already trained on a bunch of images. I give the same image to the human subject, right? And now I want to understand which part of the CNN best correlates with the V2 area in the brain of the humans, right? How do I do that? How do I answer that question? I take every hidden layer of the CNN and try to estimate the activations of V2, right, using a linear set of weights. So I take just a weight matrix. I try to fit the activity of predict the activity of V2 using the activation of the hidden layer, and I consider every hidden layer in the process. And this I do over a large number of images, which are presented both to the network and to the humans, right? And then in every case, I have to predict the activation of the corresponding brain region. And I get an error, because obviously I may not get a great fit, I'll get a lot of error. So I see which of the hidden layers gets the smallest error. So then I say that, okay, that is a hidden layer which correlates best to that brain area. So in this case, let's say V2. So this kind of analysis people have done, which is very simple to do. People have also done other kinds of more in-depth representation analysis, but I'm skipping that. So when people have done that, right, so first of all, first thing that people have observed is the overall error pattern, error levels or accuracy levels are similar between deep networks and human performance, right? The ballpark figures are the same. So you change data set, give a data set to to a network, train the network, give a data set to a bunch of people and train them to classify them. Right, the kind of error measures that you got, accuracy levels that you got in both cases are about the same, which itself is quite interesting, right? But what was observed also is that the network and the humans are not making errors on the same images. The error patterns at the individual image levels are slightly different, but average error levels are about the same for lots of deep network models. You take ResNet, take GoogleNet, you take VGG and AlexNet. There are many different deep network models that are trained on different image classification problems. Right, they all give about same overall error performance compared to humans, but individual image level, the error patterns are quite different and not quite consistent, which is interesting. So there's still something is different between humans and the deep networks. Now they look at this property, that is this deeper question, that is, are the hidden layers of the deep network correlated with the kind of hidden layers of the visual system? That is, in this case, since we are looking at object recognition tasks, we are only interested in the the ventral pathway, right? And so we look at that. so here in the left image here, what they're looking at is you look at layer 1, layer 2, layer 3, layer 4, right, from first hidden layer, second hidden layer, and so on, and calculate the correlation with V4 part of the visual system on the lines we just described. And they found that layer 1 has very poor correlation, layer 2 has better correlation, layer 3 has even better correlation, but layer 4 again is not very good, which means that an intermediate layer in the visual system it seems to behave like an intermediate layer in the CNN, which is very interesting. Because CNN is, I mean, much simpler, much more artificial compared to the real brain. But then this seems to be good enough as a model of some of the average responses that you observe in the real visual system. So similarly, if you look at the activations of the deep network, compare it with the activities of infratemporal area or IT area, which is this area. This is where the object recognition is taking place. It's like one of the final outputs, final layers. So here again, something interesting is observed. Layer 1 of the network, poor correlation. Layer 2, poor correlation. Layer 3 is also bad. Layer 4 has the best correlation. That means one of the last hidden layers of the CNN correlates very well with the IT area, which is intuitively something that you expect, right? Assuming that the DNNs are like real visual system. So you see that here. So basically, they have taken human subjects performing the visual classification task, and they take look at the activation of the brain using an fMRI. fMRI looks at the activities of the brain. Unlike MRI, it just looks at the structural properties of the brain. It doesn't look at activities. Right, so fMRI looks at activities, and using these kind of activation data from the brain, they construct these models and found out which layers in the CNN correlate best with the layers in the network. So next, let us come to auditory system. So we know that auditory system processes sounds, converts them into electrical signals, right, and recognizes these sounds. So we have given a little bit of introduction about this in the last, previously, I think when we talked about the tonotopic map. So sound enters to this ear canal, and it vibrates the tympanum, the eardrum. Eardrum then in turn vibrates these three bones called ossicles, malleus, incus, and stapes. The last one, stapes, right, bangs on this. Actually, literally, it looks like a doorknob. Right, bangs this doorknob, which then activates another membrane, which is at the mouth of this long tube, which is the cochlea. And within this tube, there is a long, flexible structure, like a rubbery structure, which looks like a tongue. Right, and also it is like tongue. It is tethered in one end and freely dangling at the other end. So when this doorknob is getting banged by the vibrations of the tympanum, it produces certain vibrations in this in the long rubbery structure, which is called the basilar membrane. And depending upon the vibration of the input, the stapes, right, the vibration in the basal membrane also occurs at a specific location, right? So, right. So if you look, so the low frequency stimuli produce oscillations or vibrations on the far end of the basal membrane, and high frequency stimuli produce oscillation in the near end, in the proximal end. So if you present a more composite sound, which has multiple frequencies, that sound produces active vibrations at different points in this basal membrane, literally breaking it down to its component frequencies and performing some kind of a Fourier transform or a Fourier analysis of the input signal. So these vibrations of the tongue of this basal membrane, right, move certain cells called the hair cells, right, and so that stretch certain other certain process of the hair cells called the cilia. The stretching of this cilia, right, activates certain sensitive channels, and therefore converts this. So sounds are converted to vibrations, vibration converted to movement, movement is converted into electrical signals, right, and so therefore you have this conversion of sound into electrical signals, which is conveyed to the higher layers. So the higher layers, just like in visual area, you go from retina to a bunch of nuclei and go to the cortex. In case of visual information, after retina, it just goes to one intermediate stopover, which is thalamus, which is LGN. Whereas in the case of auditory system, it goes to multiple stopovers. So from cochlea, which is output of your ear part, transducer, you go to a couple of what are called the cochlear nuclei, deep brain nuclei. From there, you go to another nucleus called the superior olivary nuclei. From there, you go to inferior colliculus, right, and then you go to medial geniculate nucleus or medial geniculate body, This is analogous to LGN for vision. So what is LGN for vision? MGN is for our auditory system. This is, both of them are parts of this big structure called thalamus. After that, it goes to the auditory cortex, primary auditory cortex, in both hemispheres. I'll skip all this stuff, and so basically here also they have taken a network which has takes auditory inputs, and here the network is trained on two separate kinds of tasks. So they present a short sound segment to the network, and in one case the sound segment has words, spoken words. Other case the sound segment corresponds to some musical passage, and the networks. In the first case, it's the network is supposed to classify the word. The second case, network is supposed to classify the musical genre. Okay, so thing is both for word classification and musical genre classification. The network, even if you train to separate networks, the earlier processing of in both cases is likely to be very similar. Right, keeping that in mind, these people considered a more hybrid architecture where up to a point, both kinds of information go through a common set of hidden layers, and after that they diverge, they bifurcate, and in one pathway you process the words, other pathway you process the music. And they found that so there is an optimal level up to which point you should have common pathway, right? If this fork is postponed to a much later this thing, then your performance is not as good. Okay, so again, like before, they found that higher hidden layers correspond to later layers in the auditory system, and lower layers in the CNN correspond to lower layers in the auditory system. Okay, so so that ends the discussion on the auditory system also. So I'll send both these papers, and you can go over them. It's a very interesting set of results, just to show that even simple DN models can capture several properties of responses in the sensory cortical areas in the brain. So that completes our discussion on DNNs and MLP backdrop and all that. So next class we'll have a short demo of MLP and perceptron by Sandeep, and then I'll start discussion of Hopfield network, which is a general class of networks called recurrent networks. Okay, any questions? So somebody asked some question about the biological relevance of backdrop last time. I hope they are satisfied with this data. I'll send these two papers to Sandeep and he'll share them to everybody.